All right, gentlemen, in this video, we are going to officially start talking about how to integrate or anti-differentiate by hand. And I know some of you have kind of figured out how that might work based on some of the delta math that you did earlier in this class, but we are going to officially put some rules to it now. So our topic is called anti-differentiation, aka or also known as integration, okay? So by definition, all right, if you are given, all right, dy equals, actually, let me do it like this. Dy over dx equals f of x, okay? And you do what's called separating the variables. So you get the y's on one side and all of the x's on the other, okay? Then you can integrate both sides, right? So you guys are familiar with the integral symbol, all right? You're going to integrate both sides. And then you are going to get y equals, all right, some other function, we're going to call it capital F of x plus c, okay? So that's very, very important. And you'll see why when we look at the rules. But anytime you integrate a function and you're not plugging bounds in, so I'm not talking about the fundamental theorem yet, you don't have any bounds at the bottom or the top that you're going to plug in, you must add c, literally plus c, to your answer, okay? And then keep in mind that you should always be able to check yourself, because if you take the derivative, all right, of what you just got, okay, you should always be able to go back to the original f of x, okay? So if you take the derivative of your answer, you should always be able to go back to f of x, all right? And keep in mind that anytime you take the derivative of a constant, it disappears, okay? So that's why I don't really have it written over here, okay? So let's look at some of the rules of integration, and then we will look at some practice problems, okay? So I'm going to go over several rules here, and so you definitely want to write these down and keep them somewhere where you can refer to them and study them. These are things that you are expected to be able to do. Okay, so the first one is the integral of 0 dx, okay? And so you have to think about, like when you integrate, you're thinking about, okay, what could I take the derivative of and get 0? And so then I need to go backwards from that. So if I take the derivative of any constant and get 0, then if I integrate 0, I should be able to go back to that constant, okay? And so that's why there is always a constant added to the end, because you don't know if that function had a constant at the end or not when you go to check it, okay? All right, now, what if, all right, I wanted to integrate a constant, okay? So I'm going to call this one k. All right, so I'm thinking to myself, all right, when I was doing differentiation, what did it look like when I took the derivative of it and all I got was a number? No x's, okay? Well, that's like slope, okay? When you take the derivative of a line, or, you know, just like a linear function like 3x, when you take the derivative of that, you just get the 3. So the idea here is we're starting with the 3 and we're working our way back to the 3x, okay? And so if you're integrating a constant, then you get the constant times x, and then you also need to add c. All right, so let's put it into perspective. If I had the equation of the line 3x plus 7, and I took the derivative of it, wouldn't I just get 3, whether it was 3x or 3x plus 7? And so you have to account for the possibility that there was a constant added to this function, okay? All right, now, the other option, okay, is if there is a constant in there, right, you can actually factor that constant out to the front, like we did with the pies when we did the, when we were looking at, when we were looking at volume, you can factor the constant to the front. Okay, well, if I factor the constant out of this particular integral, then what's left? There's a 1 dx left, okay? And so you can think of it as the constant stays, and then the integral of 1 dx is x, okay? And then, of course, you need your plus c. All right, so then let's think about some of the other rules that we learned for taking derivatives. We learned a power rule, so we should be able to basically undo that power rule for integration, okay? All right, so think back to your power rule, all right? So let's kind of do an example over here. Let's say I had, I don't know, x raised to the 7th, okay? And I wanted to take the derivative of it. So I would bring the power to the front, and remember, you would subtract a power, okay? So then how do I undo that, okay? Well, I would have to add 1 to the power, and then how would I get rid of the 7? Well, I'd have to divide by the power. So the rule there is, if I want to integrate x to a power, okay, if I want to integrate x to a power, then I will add 1 to the exponent, but then I have to divide by the new exponent. And then, as always, I still have to add c, okay? And there is a little catch here. You have to make sure that n does not equal -1. So what that means is when you're done, you don't end up dividing by 0, okay? There's a special rule for that. All right, number 4. All right, let's look at some of our trig, okay? So I have to think about, and perhaps it will be helpful if you had your trig derivatives handy, or any of your derivatives. Maybe you have your list of your rules, and you have to think about how do you go backwards, okay? So if I started with sine of x, and I took the derivative, I would get cosine of x, which means if I start with cosine of x and I take the integral, then it should take me back to sine of x, okay? So understand that I'm just trying to think, how can I go backwards, all right? And then, of course, you still need your plus c, all right? So then what other trigs do I know? Well, I know that if I take the derivative of cosine of x, I get negative sine of x, all right? So then what if I don't put the negative in the integral? Well, it's got to show up somewhere, so it's going to show up in the answer. So the integral of sine of x is negative cosine of x plus c. All right, well, when I take the derivative of tangent of x, I get secant squared of x. So that means I should be able to integrate secant squared of x and go back to tangent of x. Again, you just need to review your derivatives and make sure you can basically do them forwards and backwards, okay? Let's see. When I took the derivative of secant of x, I got secant x tangent x. So I should be able to integrate secant x tangent x. You always have to have your dx, and that will take you back to secant of x. Okay, plus c. And then I'm going to do the same thing for cosecant. All right, if I started with cosecant and I took the derivative of it, I would get negative cosecant cotangent. All right, but what if I don't want to put the negative on this side? Then it ends up on that side. And then, of course, you need plus c. And then what was the last one? Okay, I know how to take the derivative of cotangent. That gave me negative cosecant squared. So I should be able to start with cosecant squared when I'm integrating. And that will take me to negative cotangent of x plus c. All right, so it really is, I can't say it enough, a matter of knowing your derivatives so that you can basically undo them and go backwards. All right, now there are a couple more that we have learned. Remember, we learned how to take the derivative of e to the x, and it was e to the x. So I should be able to integrate e to the x and go back to e to the x. But I need a plus c. All right, and then one of the other functions that we spent time looking at was we learned how to take the derivative. All right, we learned how to take the derivative of natural log of x, right? If I take the derivative of natural log of x, hopefully you remember you get 1 over x. Okay, so that means I should be able to start with 1 over x, and that will take me back to natural log of x. Now, you do have to put absolute values around the x just because you can't take the natural log of a negative number. So you always put the absolute value around it when you work it in this order. All right, and then you need your plus c. Now, I want to show you something else with this one, okay? Another way to write 1 over x is to write it as x to the negative 1, okay? Well, then that kind of looks like the power rule. But what happens if I apply the power rule, which means I add a power and then divide by the new power, right? What do I get when I add those two things together? Then I have division by 0. And that's how you know, like just the fact that you can't divide by 0 is how you know that this is a special integral. Okay, it has its own special rule, and it is the natural log of x. Okay, so I just wanted to point that out. So that's why there's that special circumstance on the power rule. All right, let me go all the way back up here. There's that special note on the power rule that the original power, the n, cannot be negative 1, right? Because that would force you to divide by 0. So if that original power is negative 1, all right, then you need to think something completely different. That's the natural log of x, okay? So hopefully that you will remember that because you can't divide by 0, okay? All right, so I'm going to actually stop this video here and then make a second video of some examples of me going through these, and then I'm going to give you some, I guess, some practice problems from the book that you really should look at to make sure that you understand the rules, okay?